Okay, so I'm going to record lecture 14, where we continue our study of CNN or ConvNet. So for the convolutional neural network, I use this plot to illustrate the basic idea where we focus on the notion of neural network as a team of vectors. So for convolutional neural network, we have multiple layers of vectors, and the vectors at the lower layer are more densely planted, and the vectors at the higher layer are more sparsely planted due to regular subsampling. So you plant each vector every, say, 5 pixels and so on. So depending on your subsampling rate. And also, as you go up, the dimensionality of the vectors become bigger. And eventually you have a single vector because of the subsampling, so that from this vector, you can go through a few steps of multi-layer perceptron, so that eventually you can do classification, computing the logic scores for all those categories and translate them into probabilities for classification. So that's a basic idea. And here at each layer, we have like a map for thought vectors. And those vectors at the higher layer are spatial compositions for the thought vectors at the lower layer that are nearby, so that higher layer vectors cover bigger range and see bigger patterns. So they are more complex, and that's why they need higher dimension to absorb or to contain the information. But at the same time, because this flow is from image to the category, so gradually, if you go up, those vectors are more concerned, or they are more about the category instead of the image, so that they throw away more and more irrelevant details about the image, and they keep those information that are relevant for the category, so that eventually you can even imagine at the top layer, very top layer, if you keep training the network, and even after you get zero training error, you keep training it. So it is possible that for each category, all the vectors at the top layer will converge to a single vector. So it throws away all the information about the image details and only keeps the information about the category. Okay, so therefore, from this perspective, the higher layer vectors are also more abstract than the lower layer vectors, or they capture more essential information and throw away those irrelevant nuisance details. And in terms of notation, we use this key equation to denote convolutional neural network, where we use ij to denote the position where this vector is planted, and y. So here y is the vector at this layer, and x denotes the vector at the lower layer below, so that yij is actually a composition of those vectors that are near ij with this type of small range of shift. For example, delta I, delta j may belong to -1, 0, and 1, so that we have 9 positions, right? So we combine the x vectors at these 9 positions. And then we can write yij, which is a vector equals a matrix that depends on the shift delta I, delta j. So it's a matrix times the vector at shifted location, which is I plus delta I and j plus delta j. And then we can also add a bias and then rectify. So here I use this wave hand notation. This add rectify means that after you compute this linear, right, linear values. You then apply ReLU or sigmoid or tan or whatever you can think of, those nonlinear transformation to each element of this vector. Okay, so this is a rectification, and I just use add rectification, means that you then add the operation for element-wise rectification. And we know that this rectification is very important, right? So the ReLU rectification leads us to this piecewise linear approximation, which can be a very good approximation to any continuous and smooth function. So this is a notion of composition. So the y vector is a composition of x vectors planted nearby. And so here, each layer corresponds to a box. For example, we have x box, those are the x, and then we have y box, those are the y. So here we plot the vectors horizontally. So this is our yij, this is our xij. So this is another way of understanding this illustration. For example, we may have 10 channels, so each vector is 10-dimensional. And here we may have 100 channels, so each red vector is 100-dimensional. And this y vector is a composition of the 9 x vectors at the layer below, so that for each channel we have a feature map, and at each location we have the feature at this location for this channel. So each channel supposedly captures a particular type of feature, and then this vector consists of all those different channels. We know that later, after this convolution, we can also perform subsample, so that we don't need to keep all the details, because yij is nearby yij. They have a lot of overlap, right? If you have the kernel of this shape, they may have a lot of overlap. We don't need to keep them to reduce the computation, and also maybe to avoid overfitting. So after subsample, we then repeat these steps. So the subsampling make those vectors more sparsely planted, right? Because of the subsample, you only keep a subset of it, and you keep doing that until you get the top layer, which enable you to make a prediction. So I think this is I hope that this give you a clear explanation for this convolutional neural network. And in particular, I think this idea of a team of vectors is quite important. So it's very much like, say, a team of football, right? Football team. You have this those team members, and then they pass the ball or pass the message. For example, those x vectors pass message to y. So you keep relaying the message and until you make the prediction. So you can think of this whole process either as a form for representation or modeling. So different layers, you have vectors representing different patterns with increasing complexity and abstraction. But you can also think of this as a matter of computation, right? You do this computation step by step, and eventually you are able to make a prediction. So the idea of convolutional neural network was inspired by this visual cortex in our brain, the architecture of visual cortex, where there are operations cells that doing operations at different locations, and they share the same type of operations at different locations because objects can appear at different places. So Lacan was the inventor of convolutional neural network, and the network he invented is called the net. Currently, the convolutional neural network still adopt a similar architecture. So the LeNet was invented in the 80s, and it was applied to MNIST dataset, which consists of 6,000 handwritten digits, and the image is 28 by 28. And in 2010, there's a DANet, which uses GPU for parallel computing because the convolution can be done in parallel. And they also use a bigger model so that they get a very good result on MNIST. And then in 2012, AlexNet was invented, and it was applied to ImageNet, which is a much bigger data set than MNIST. MNIST has 10 categories, right, corresponding to the 10 digits. But ImageNet has 1,000 categories, and with 1 million training examples, they're also a much bigger version. So the data are collected through this Amazon Turks. So you ask people on Amazon to label the classes or categories of the images for you. And AlexNet in 2012 won the challenge or competition on ImageNet object recognition by a big margin. So that actually started the explosion of deep learning. And even though deep learning, or maybe we should say neural networks, experienced some near-death experience early on, but now because those deep learning models, they can even achieve superhuman performance in some scenarios. So I think it will keep going. I don't see any slowing down in this field, and it also has been applied to many different fields. And then later, people in Google developed LeNet, Google LeNet, which is really paying a tribute to LeNet, earliest LeNet, where they use 1-by-1 convolution, as we discussed. So there's only at each position, right, you perform this transformation. There's no spatial extent, and then 3-by-3 filters like this one, and then 5-by-5 filters, and then concatenate them, combine those feature maps, and then keep going. So this network is quite deep at that time. I think more than 20 layers. And later, this 1-by-1 convolution actually inspired the development of Residual net, as we shall discuss later on. And then the VGG group in England also developed a version where they only use 3-by-3 filters, and they have one 16-layer version and one 19-layer version. And they also apply this to ImageNet. And after training, they release the trained weights so that the people can use the trained weights to compute image features. That is, to compute those vectors. For each input image, we can compute the vectors at multiple layers. And then we can use those computed vectors as extracted features for some other tasks. So therefore, we can think of VGG as a matter of pre-trained model, which serve as a useful feature extractor, so that we don't have to engineer or design our own features or handcraft our own features. We can just use the pre-trained model. If my memory serves me, this I think VGG has 64 million parameters. I'm not sure whether that's a correct number. At that time, it is a rather big model, although nowadays, that's not considered to be very big. So when VGG group released their trained weights, it is actually very good, work very well. However, at that time, other people have difficulty to train the network with the same accuracy or effectiveness or usefulness. But later, I think people develop this batch normalization so that it become more of the science. So that when you train your network, you start from different random initializations. and then different people, of course, they train different weights, different size of weights, right? But those weights often have very comparable performance, so that you get same result, same behavior. So therefore, this is a very important invention to make the training for deep neural network into more like a science or technology instead of alchemy, right? You just try and hope that you're lucky enough to get a good set of weights. The idea of batch normalization is very simple and also very insightful. So suppose we have multiple examples. In each example, for each training image, right, we have multiple layers of vectors or multiple boxes. And here I use this box illustration. So at a particular layer, for example, this X layer, we have a box for example 1, and we have another box for example 2, and we have, suppose we have 100 examples in our training batch, then we have 100 boxes. And at each channel and at each particular position, so we have a feature, let's call this X1 for the example 1. And at the same channel and same position, we have X2 for example 2, and then Xm for example M. So always at the same channel, same position, we then collect a batch of features values. And what we do is we normalize this over this whole batch. So we compute the batch mean, the average, right? And then batch standard deviation. So that is, we sum over each xi minus x bar, the mean, square them and divide by m, and then take square root. So this is a standard deviation. And so that we have this, let's call x1 head, x2 head, and so on, which are computed by, for each xi, we subtract the batch mean and divide by batch standard deviation. So this gives us a standardization, right? And then if you look at this whole batch, then the mean of those xi head will be 0, and the standard deviation of xi head is 1, so that the overall statistics of the overall distribution is fixed, no matter what the parameters are when you use to calculate those x1, x2, and so on. So the insight or the rationale for this batch normalization is that after this normalization, then if we input this xi hat to the next layer, to, for example, from here we do batch normalization, and then we use a normalized version of x. So we do this for each channel and each position, okay, over the batch, and then we have this batch normalized box, right? And then we let this to be the input to the next layer. Now you see that no matter what are the parameters or initializations you use to compute this box, the input to the next box after batch normalization always have overall same statistics. It's very stabilized, so that the next batch always receive the input with the same statistics, mean and variance over the whole batch during the training process. So this somehow stabilizes the so-called covariate of the input. So we sometimes in statistics, people call X the input to be the covariate, and then you learn to compute Y from this X, right? So you, by this batch normalization, you avoid the covariate shift, so that you make the training more stable and also more efficient, so they converge hopefully faster. So this is idea for batch normalization. So it makes the training of the neural network more stable, so that people with different random initializations often learn networks of different ways, but very comparable performance and behavior. Okay. So people also use BN to abbreviate this batch normalization. So you can insert this batch normalization after the weight layer, and then maybe before the ReLU layer, or there's different ways of doing that. But the key idea is to avoid the overall shift of the statistics of the input X. Okay, let me go to the next page. And we can also add another like a layer of just learning a linear transformation. Say we let yi to be beta xi hat after normalization plus a gamma. We can also learn beta and gamma along the way before input to the next layer. Okay, so we can also add this step, but the key step is the normalization. And when you train the network, there's some complexity in the sense that each xi hat is computed from multiple examples in this batch. Okay, from all the examples in this batch. It's not just computed from xi itself. Okay, so xi hat not only depends on xi, but also depends on x1, x2, and xn, all those xi, or x1 to xn. So therefore, when you do backpropagation using the chain rule, right, you need to actually backpropagate to all the training examples. So it is as if each batch is a single training example. So that's the complexity for batch normalization. So to avoid using the whole batch, people also develop this layer normalization. So suppose this is a single layer of X, you can just, for each training example, you can just normalize each feature, say Xij, right, by all the values, all the features in this layer, or maybe in the same feature map. And you can just tune your code to see which normalization give you a better result. So this layer normalization also stabilize the overall distribution for the input to the next layer. But here we normalize, for example, for this this feature, we don't normalize of the same feature against same feature of other examples. We just normalize this feature against other features of the same example. Okay, so therefore you don't need to do this type of backpropagation. And the layer normalization has been very commonly used in the transformer model, as we shall discuss later on. But the overall rationale for layer normalization is essentially the same as batch normalization. We want to stabilize the input to facilitate the training and so that it may have very good performance. Okay. And then nowadays, when people work on computer vision problems, instead of using the original LeNet convolutional neural network, people use a modified version of LeNet, which is the residual network. So in the conventional CNN, such as LeNet, so the next layer, let's call this XL plus 1. I just use X to denote a particular layer. We may also use H if you want. So here, just for simplicity, because we are not really distinguishing between those things, we just use X as a particular layer. For example, this is our X. And the next layer, let's call this XL plus 1, is a transformation, right, of the layer below. So this transformation may consist of a weight layer. So you just use a spatial composition with those matrices like a W, delta I, delta J, right? And then plus batch normalization and plus ReLU ratification. So this is a conventional CNN, and you can use as many layers as you can afford, as long as you can train the model reliably. But the ResNet use a different parameterization. So it parameterizes capital F sub L to be XL plus small f sub L of XL. So this is small f, this is a parameterization of the neural network with a weight layer and batch normalization and ReLU. What's important is that we just copy the layer below. to the next layer and then add this correction. So this is called a residual. So you're not just copy this the layer below. You also need to add what's left. You add the residual. This can also be considered as a correction or refinement. Okay, so here, in order to perform this, so both XL and XL plus 1 should have the same, right? The same shape. Otherwise, you can also use a one by one convolution, right, to change the number of channels. And you can also add subsampling to change the size. So those are all doable. But within the same block, which we call residual block, so this XL and XL plus 1 should be for the same shape. They have same number of channels and the same size of the feature map, so that you can add, right? So the next layer, first, when you compute the next layer, you first copy the previous layer and then learn the residual again by the regular convolutional neural network. So nowadays, when people use CNN, often they use the ResNet version, which is a reparameterization for CNN. So in terms of expressiveness, this big F and this small f plus XL, so they express the same thing, right? Same class of functions mathematically. However, in terms of training, this residual network has much better behavior or properties. So usually people plot the residual network in this way. We have XL and we want to compute XL plus 1, right? So you first copy XL and then you use a neural network, weight layer, Bayesian normalization, or ReLU, or whatever order that you can think of, to compute the residual. So you add XL to this F of L to get XL plus 1. Okay, and then when you do bipropagation, you see you now have two branches. People call this as a skip layer because this skip connection, because this connection you skip all those layers, right? You directly copy XL to XL plus 1 and then add the residual. So this was inspired by this one by one convolution for Google Net. And then when you do bipropagation, you need to bipropagate along this path, right? But you also need to bipropagate along the skip connection so that the information can pass down very quickly. So that's a feature of this residual network. So just to intuitively understand why does the residual network perform better than conventional network. So there's some explanations or understandings that make some sense. For example, in the neural network, we have ReLU, right? ReLU network. But the ReLU is a two-piece linear, right? So here you have 0, and here you have this just keep the value. On the positive part, it's just identity. That is, you just copy what are value that is positive. So this type of bending is very important to make the network nonlinear and or piecewise linear to be expressive enough or flexible enough to approximate any nonlinear relationship. But ironically, by being so flexible, it is not really good enough to approximate this identity, the pure identity, because of this bending. So ReLU seem to have a hard time to learn this the simplest identity mapping. It is like you can solve a very difficult problem, but you forgot how to solve 1 + 1 = 2. And then for that matter, we just add this identity mapping directly to the ReLU network so that we only let ReLU to capture what is above this identity mapping to chase those difficult problems. So leave the simple problem to this identity mapping. So that's one explanation. And another explanation is about the landscape of the loss function. suppose we use the least square loss or this cross entropy loss for classification, which is a negative log likelihood. And then the loss function over the parameters may be highly multimodal. And it is also possible that, in this shape, so here you have the so-called gradient vanishing problem. Your gradient becomes 0, you don't know where to go. Here in this part, you have gradient explosion problem. The gradient is just so big, you suddenly go to a different place. Usually gradient vanishing is more common if you have multiple layers. So when you pass the gradient back in the backpropagation, if you pass gradient along this route, then the gradient can quickly become 0. But because of this skip connection, you can pass a gradient also along this route, so that you pass this identity mapping. So that's the understanding. But actually, apparently, even for a deep network with batch normalization, already you don't seem to suffer too much of gradient vanishing problem or gradient explosion problem. So the main problem may still be that the network is very multimodal. So you can easily be trapped in a very suboptimal local mode. So that's the problem with a regular CNN. So with batch normalization, hopefully the situation become a little bit better. And this may be a little bit too idealized, right? So unimodal and almost like a convex at near the mode. But the hope is that the landscape is much better behaved. Okay, so at least it is less multimodal. And so this is another understanding from the perspective of loss function, the landscape of the loss function. And I think maybe I would say the best understanding of residual network is to treat it as a iterative algorithm. So within each residual block, you keep doing this updating. So instead of thinking L to be the layer, you may think L to be the time t for a iterative algorithm or a recurrent network. So that it is still the same, just the same like a box, but you keep updating the values, or it is still the same, the same vectors, but you keep updating the vectors. So it's like each those vectors keep thinking for themselves. It's a thinking process. Instead of just one step, you use multiple steps to update those vectors. So that's the idea for residual network. So each residual block learns a iterative algorithm. We know that an iterative algorithm is often in the form of this refinement, right? So xt plus 1 is xt plus some correction or refinement. For example, in gradient descent, so this at the current xt, you take the gradient. So your ft is like the gradient, although we don't really learn the original loss function. So that's the point. So this iterative algorithm may be doing gradient descent or some other optimization algorithm to minimize a certain loss function or optimize a certain objective function, but we don't know what exactly this objective function or what's exactly this loss function. We just learned this algorithm, say 10-step algorithm, and then after 10 steps, so we get the set of features, and then we can move on to pass to the next block, residual block, and then again doing this iterative type of computation. So for example, you start from the image, and then you have this residual block. You may have 3 residual blocks, which means those vectors undergo 3 steps for updating, and then you do subsample, and then you go to the next residual block. You do nice, for example, 9 steps for updating. Okay, and then going next block. So then there's the issue of how many residual layers, right? How many residual layers you want to do. So here, this residual block we may do 9 update, and this residual block we may do 3 update. So this is also a design issue, and currently people use residual 18, so 18 residual steps, or residual 50 or residual 200. Residual 200 is quite a big network, involve 200 steps of computation. Okay, and also as I mentioned, if you do gradient descent or compute backpropagation, then the derivative for xl plus 1 over xl, right? If you compute the partial derivative, you have the axis identity because of the copy of xl and plus the derivative here. So you pass the derivatives along 2 routes from this skip connection. You pass this identity. So this is not 0. So this may avoid gradient vanishing. Okay, so that's the main idea of residual network. And maybe I can go back to the original plot for this team of vectors to just further explain it. So let's see if I can go back. So sometimes it's not that as easy to do. Let's go back. Seems difficult. Okay, I cannot go back. Let's see if I can do, but maybe I will move on. So just remember that when you have CNN at the beginning, right, we have a team of vectors at multiple layers. So the point is that for each layer of vectors, it undergoes multiple steps for operations, and those operations may have different weight and bias parameters. Okay, so it's like each layer those vector sync for a few rounds, a few steps, and then pass the information to the next layer. So this is like a iterative algorithm. Okay, you mimic an iterative algorithm. So this actually brings us to the so-called recurrent neural network. So that is things happen over time. Although for image, actually, we just observe an image, one image at a time, right? But if you think about the video, we actually observe those image over time. So at each time point, the image is called a frame, a video frame. So things happen over time. More importantly, for language, right? We speak over time, or when you write the text also is written sequentially. So there's a temporal dimension. So for the spatial dimension in the image, we use a convolutional neural network. But for the temporal dimension of time, we use this so-called recurrent neural network, so that we have the input, which we call x1, x2, xt minus 1, xt, and so on. And then we have output, y1, y2, yt minus 1, yt, and so on. Of course, sometimes we may not have output, and sometimes we may not have input. But for neural network, we always have hidden layers, h1, h2, ht minus 1, ht. So if you think about a regular multi-layer perceptron, we have xt, and then we compute ht from xt, and we may have multiple layers for h, right? And then finally, we predict yt. So this is a bottom-up multi-layer perceptron. You can even make a convolutional neural network for this one. But for recurrent network, there's also a temporal connection. So that is this ht, the hidden vector. For simplicity, let's now just think of this ht as a single vector. So this ht not only receive input from xt, but it also receive input from ht minus 1. So that is h for the previous time step. Okay, so actually we are talking about the same vector, but the vector keep changing over time, and the vector receive input from itself at the previous time. So that's why it is recurrent. It's called the recurrent neural network. So here, those vectors, okay, they are the keys to the recurrent neural network. So this HT, the hidden layer, also receive the information from the previous time step. Okay, but here I want to somehow clarify an issue, is that it doesn't mean that this YT not only depends on xt minus 1, okay, only depends on the input from previous step, because this ht minus 1 not only take input from xt minus 1, but it also take input from ht minus 2. Okay, so you see there's a relay of this information over the whole history. You may start from h0, which is often just all0 vector, okay, meaning that there's no prior information whatsoever, and then you start to pass this information. So therefore, if you look at ht actually absorbs the information not only from xt, but also from xt minus 1, and moreover from xt minus 2, because xt minus 2 input ht minus 2, and ht minus 2 input ht minus 1, which in turn input to ht, right? So essentially, ht captures all the information from the past, and ht actually capture the information for the purpose of predicting yt. So it captures all the information from the past for the purpose of predicting yt. Okay, so that's the point of view of recurrent neural network. So the one limitation of this recurrent neural network is that HT collects information from the past only through this path. So it has to get information from HT minus 1, and HT minus 1 has to get information from HT minus 2, and so on. So you have to relay the information, pass a message over time. HT cannot directly get information from X1 or from X2 and so on. So that's one limitation. So later, the transformer architecture will avoid this purely sequential feature or sequential architecture, so that HT can pay attention to all the other inputs at other time steps. But for now, let us still focus on this architecture, but knowing that HT actually capture all the information in the past up to time t. Okay, all the information here in order to predict yt. Although, as I mentioned, it collects information from the past, not directly but indirectly from the previous age. And also, as I mentioned, this is happen over time. So we only have a single age, but age keep changing over time. It is very much like a thinking process, right? A process. You keep updating your thought. Again, you can think of this as a thought vector, and you keep updating your thought. And so for this architecture, it is still like a multi-layer perceptron, except that it has a little bit more sophisticated architecture according to this tempo connection. And then we can still use the language, mathematical language for neural network. So this vector matrix multiplication plus element-wise rectification to express or to describe this Rn. So for the vanilla Rn, we have HT to be we have W, a weight matrix multiplied by the concatenation. So you just put two vectors together, concatenate them. So you have HT minus 1 and XT. And then you multiply this by a weight matrix for compatible dimensionality. And so here I just use W as a generic notation. So they may differ in each occurrence. And then you do element-wise rectification. And then you get your HT. So that's the structure. And as the input, so as the output YT is just another like a rectification from this vector, essentially the same as a multi-layer perceptron, right? Because you have vector here. After one step or a couple of steps, you can then predict YT, similar in the multi-layer perceptron. Okay, so now let me go to the next page. Oh, okay, so here is the plot here. Okay, so that is this thought vector, right? This thought vector keeps thinking about itself. It receives input not only from xt, but also receive input from the value in the previous time step. So this is the process. And if you use continuous time, it is like very much like a differential equation. So here, sometimes you may not have input And sometimes you may not need to output the produce output, okay? But you always have this recurrent connection. So HT always receive input from the previous time step. So that's a basic idea, a sort process. So we use RN to approximate a sort process. Okay, so somehow let me see if, okay, let me go next page, please. Allow me go to next page. Okay, so okay, so next page. Huh. Okay, so that sometimes you have to put up with those computers. Okay, now it seems we could, finally, okay. And what about the rectification and the transformation? So the transformation, you see that we concatenate HT minus 1 and XT as we described before. And then we have this matrix, we multiply this matrix to this concatenated vector. So you have two pieces, right? HT minus 1 and XT. So correspondingly, you can divide this W into the two parts, WH, which operates on HT minus 1, and WX, which operates on XT. So supposedly, this dimension should be the same as this dimension, so that you can perform matrix vector multiplication. This is plotted in a non-proportional way, but it's okay. Let's just, so we know that this dimension is the same as this dimension, and this dimension is the same as this dimension, so that this matrix multiplication can be written as WH times HT minus 1 plus WX times XT. Okay, so that's the main part of this neural language, right? Neural network language. We have matrix vector multiplication. As to the rectification, often people use the tan rectification. So the tan rectification is that is this form, EX minus E negative X divided by EX plus E negative X. So it is similar to sigmoid. It goes from -1 to 1. So this serves to keep this HT, each element of HT within a certain range. And it can be quite important. Of course, it also gives us piecewise constant type of approximation. And then after we compute HT, we then get YT to be computed from HT by a multi-layer perceptron. For example, we can multiply W to HT. So this W is another W, different from the W here. And then we do rectification. Or we compute W, multiply W to HT, for example, for the matter of classification. So that WHT gives us the logit scores, a vector of logit scores. And then we can perform softmax to get the probabilities for those different categories for the purpose of classification. Okay. So for the vanilla version of RNN, just like the traditional convolutional neural network, they suffer gradient vanishing problem in this backpropagation, because now we have this pass over time, right? Not just a forward pass, but also the pass over time. So if you do backpropagation operation, you need to backpropagate over time. And for that matter, the gradient can be quickly become zero over time after a small number of time steps. So a solution that is extremely influential and now like universally used is this long short-term memory, or LSTM. So this is a very popular neural network for RNN. So it introduced a vector CT. Each element is called a memory cell. So this CT is the same dimension as HT, the hidden vector, sort vector. But here we have this CT, this vector. So it serves the purpose of memorizing things from the past in a way that can be useful for predicting the future. So for this architecture, we actually introduce other vectors, again, same dimensionality as this HT. we may call HT, the dimensionality of HT, as a model dimension. And this model dimension may be, say, 300 or 500. So each vector is 300 dimensional or 500 dimensional. And all those vectors are computed from the concatenated version of HT minus 1 and XT, very much like in the vanilla network, where we compute HT from this one, right? But instead of computing HT directly, we first compute some vectors from HT minus 1 and XT. Using this operation, again, we multiply this vector, concatenated vector, by a matrix for compatible dimension. And then we perform element-wise rectification. So this vector ft is called forget gate. It's computed by this sigmoid transformation for a W matrix times this concatenated vector. And this gate, this vector for input gates is computed by sigmoid of another W for this shape and multiplied to HT minus 1 and XT, the concatenated vector. And this OT is a vector of output gates. Is computed as sigmoid of yet another W, the weight matrix multiplied to this concatenated vector. And then we have this delta CT, which is update. It is tan transformation, just like this hyperbolic tan here, right? This tan rectification for a force matrix W times this concatenated vector. Okay, so here I want to make it clear that each vector is computed by its own matrix. So we have 4 vectors, and then we have 4 matrices. Okay, and after we compute those things, we then update this memory cell. So this memory cell supposedly to keep the past memory, but also we also need to absorb what's happening right now, right? So this is modeled by this line, this equation. So the CT, which is the vector of memory cells, is FT, this vector FT times CT minus 1. CT minus 1 is the memory cell at the previous time step, and plus this IT, this input gate times delta CT, the update, how much we want to update. And here, this O dot, we call this O dot, a circle dot, means that we compute the product of this element, and then compute this product, this element. So that is everything is done element-wise product. Okay. So here you see if ft at each element, right? If this ft is 1, then you just keep this ct minus 1. And if it equal to 0, you don't update. But if it equals 1, you also add this update. So in the gate list version, if ft and it are always equals 1, then you have the special case where ct equals ct minus 1 plus delta ct. So this actually is the residual net. So we can think of the residual net as a gate list version for this LSTM, which actually was invented in 1997, and residual net was introduced in 2014, I think. Okay, so so we have those gates. You see, after computing those gates, we decide how to update CT, and then we have HT. We get this HT from this OT. So this is output gate, right? OT, and then element-wise product for this rectified CT, for example, 10 CT. But in any case, you can do whatever you feel appropriate. But here is a key idea. And then after that, we have the same as before. We have YT to be a rectification of W times HT, a different W, of course. So here, if you look at this network, so still you keep you have HT minus 1 and XT as an input, right? You concatenate them, and eventually you get your HT here. So HT is still computed from HT minus 1 and XT, very similar to the vanilla neural network. However, in the vanilla neural network, HT is it's just this matrix multiply this one and rectify. Too simple. So rather we go through 2 steps to get the HT. First, we compute those gates and updates, and then we update CT, and after update CT, we then get HT. So you have multiple steps. And those gates supposedly they very much like if-then type of things in the programming language, right? And each element is a gate, like asking a question and decide what to do. So very much like if-then. So therefore, this whole process, like here and here, these 2 lines are like mimicking a programming language or a computer code, a piece of computer code. And those gates, supposedly they are binary, but to make things continuous and differentiable, which is important for backpropagation training of neural network, we use sigmoid to mimic this binary gate. And we use 10 to rectify this update to keep it within a certain range. Okay, so this is the basic idea for LSTM. So originally, LSTM was invented to really address this problem for gradient vanishing. Just like in this special case, the gateless special case for residual net, we show that if you compute the gradient, then the partial CT or partial CT minus 1, you have this identity. So, and plus the rest, right? You always pass on this identity, which hopefully solve this gradient vanishing problem, so that you can pass the gradient, meaningful gradient, with the important learning signal for a lot of steps, so that you can train a very good recurrent neural network. So the idea is that instead of developing those algorithms, for example, those Newton algorithm or quasi-Newton algorithm, whatever sophisticated algorithms to find the local or either local or global, which is rare actually, minimum for the loss function. You better improve your model. So improving your model actually make things much better, so that even you just use the original like a very simple like this SGD, right, stochastic gradient descent, sometimes with some momentum, you can still pass the gradient very easily. So that's the original motivation for this LSTM, and it actually enables the training for recurrent neural network, non-trivial recurrent neural network. So that's why it is so important. And but from the, so here this from the backward pass, right, for back propagation, which is certainly extremely important. But even from the forward pass, you can see that now instead of computing this HT directly from HT minus 1 and XT by this very simple linear transformation, you are now introducing those gates and memory cells. So therefore, the dependency of HT on HT minus 1 and XT is much more flexible and much more complex and much more expressive. So this expressive model, a forward model, actually is completely consistent with the efficiency of this backward back propagation. So, and it is also very reasonable, right? You keep a memory and you determine whether you want to erase the memory or you keep the memory, and whether you want to update or just keep the memory intact. So it is a very reasonable model from the forward perspective, and often a good model for forward path can lead to a more easy, efficient learning based on this back propagation. Another issue or lesson that we can learn from both residual network and this recurrent network is that the distinction between computation and the representation in deep learning is actually very blurred. So you can think for the residual network, for example, each residual block as a multi-step algorithm. instead of multi-layer network. So you do multiple steps of computation for a single layer of neural network in each residual block. So this is in each in each part of the residual network, right? So sorry, I think I may use the residual block in a different way. Here, I mean the block consists of multiple steps for residual operations. I think the original meaning of residual block is that a single step. I'm sorry for this using the wording type of confusion, but here I mean each block. Maybe let's call this each big block consists of multiple like residual operations. So that you have multiple steps. So you can think of this as multiple steps of operating on the same vector. And this recurrent network is even more so, right? It just models the process directly. So therefore, sometimes one lesson from the deep learning is that you can model the computation, and the boundary between, or the distinction between computation and representation is not really that clear. Okay, so I think maybe we can stop here. In the next lecture, I probably will give you more details for this RSTM, and also a related network called recurrent gated units. Okay, so we can stop here.